Dear students, welcome and thank you for tuning in. We are continuing our discussion about composites. In this video, we are going to continue our discussion of the classifications of the different types of composites. In the previous video, we talked about the particle reinforced composites. In this video, we're going to talk about the fiber reinforced composites. Technologically, the most important composites of all the different classes is actually the fiber reinforced composite. It's one of the most important forms, and there's a lot of technologies and a lot of development in that field. Fiber reinforced composites are subclassified by the fiber length, which is a very important and critical in deciding the properties and the applications of these fiber reinforced composites. We have something called the critical fiber length, and we're going to talk about how we calculate this critical fiber length. Now, the critical fiber length is necessary for effective strengthening and stiffening of the composite material. If the length is lower than that critical length, the composite is not going to be having the strength that we are looking for or the stiffness that we are looking for to add to the matrix phase, which is the other material, if it's a two-phase composite. Now, this critical fiber length is very important to identify and it's very important to enforce. Now, this critical length depends on the fiber strength, the diameter of the fiber, and also it depends on the fiber matrix bond strength, or in other words, we can say that's the matrix shear yield strength. So if we have the matrix phase and we have the other material phase, which is we called before as the dispersed phase, because they're phases, if they're large phases, we have shear between them, and that's a critical player in identifying the critical fiber length for the material that we want to use. If you look at the pictures on the slides, so we have two examples of these fiber reinforced composites. Well, remember that all of them are aligned continuous fibers. So here in this image here, we have the metal. So the matrix here is the molybdenum, and the fibers are made of the nickel aluminum brittle material. So we have these two different phases that creates our composite, and forming this composite is actually by eutectic solidification. And eutectic solidification is happening when you have a homogeneous mixture of two substances. Both of these substances solidifies at a temperature below the melting point of each of them alone, of the molybdenum and the nickel aluminum. On the other side, we have the glass silicon carbon fibers formed by something called the glass slurry. And slurries are a mixture of solids denser than water, and they're suspended in liquids, usually water. That's how they are being formed. It's very important to keep in mind that because of having this the fibrous materials inside, let's say the matrix phase, we are getting different properties, and one of the important properties that if there is a fracture, it's not going to be a catastrophic fracture. We are changing or modifying the elastic modulus and the strength of the material by having this fiber reinforced composites. So this is just a general idea about fibers and what are they and how they are used, and some pictures of them in fiber reinforced composites. We talked about the critical length, but also there's another characteristics of these composites, which is also related to the fiber length, but we would like to make sure that the critical length is measured using a formula that is relating the stiffness of the fiber strength with the fiber diameter and also the shear. And in order to have something called continuous fibers, or the material is a continuous fiber reinforced composite, the length of these fibers has to be at least 15 times the critical length. So it has to be very long. Now, and we call this material as a continuous fiber reinforced composite. Now, other materials which are considered discontinuous or short fiber composites have length shorter than the 15 times the critical length. And that's very important. Keep in mind that the critical fiber length depends on the fiber strength, the diameter, and also the shear between the two different phases, the matrix and the dispensed material with it. If you look at the images here, so this is an example of a discontinuous random 2D fibers here. So we're looking at the surface, and the random, it means that they are not aligned. So the arrangement or orientation of the fibers relative to one another is random. So we can have two things. So either you have a parallel alignment of the longitudinal axis of the fibers in a single direction, or you can have a totally random alignment. This is one of the random alignment, and it's discontinuous, which means that the fibers are short, way shorter than the 15 times the critical length. They are processed, then they burned at 2500 degrees Celsius, and you can find this type of composites in disc brakes, gas turbines, exhaust flaps, and nose cones. And you can also find other variations of this material here. We're looking at two-dimensional, so it's an area, cross-sectional area, and that's why we call it discontinuous, because they're short, and it's random because they're not aligned on a specific direction, and it's 2D because it's an area. You can have discontinuous, which is short, random alignment of the fibers, and in 3D structure like this here. And you can also have discontinuous, which is short in 1D, fibers aligned together in 1D, and they're just in one direction. So in this video, it's good to keep in mind that we are learning about the critical length, and we're learning what discontinuous, random, two-dimensional fibrous composite means, and how to identify them. And continuous, they need to be longer than 15 times the critical length. Thank you for watching. Until the next video. Bye.